Hi, good morning, and welcome to this session. I'm Giuseppe Fiameni, and I will present you the NVIDIA data loading library. I'm the lead engineer of the NVIDIA AI Technology Center in Italy, and will introduce you how to improve the data loading pipeline of your deep learning workflows and why this topic has become so important over the years. Deep learning owes access only partially to the architecture of the networks. The other reason for this is the availability of high-quality data to achieve higher accuracy. Networks heavily rely on large datasets also to avoid overfitting, which is the characteristic of a network to model the training datasets too well and lacking generalization. Furthermore, application domains which do not have access to much data, such as medical images, need to encompass data augmentation techniques to enhance the size and the quality of their datasets. However, working with a very large dataset is not that simple, as different challenges may exist. If you take this typical deep learning workflow, it starts from the data stored on the hard drive, continues with the pre-processing phase, and eventually conclude with the training. In this case, the goal of the pre-processing is to constantly batch the model with data. But this workflow has changed a lot over the years. Initially, before the advent of GPUs, most of the time was spent during the training phase. The preprocessing part was not a problem, as CPUs were relatively slow while processing data. The availability of accelerators and the capability to move data from the CPU to the GPU via CUDA dramatically changed the scenario and provided a significant boost into the performance. By then, the main factor determining overall performance was the time spent in moving the batch to the model. And under these new conditions, the overall performance is linked with the time invested in moving the data from the hard drive to the model fast enough to keep the GPUs busy. In this case, you can see two GTX 580, exactly the cards that were used to train AlexNet. The situation became even more critical when networks could be trained across multiple GPUs or multiple nodes. With respect to the preprocessing phase, the training of a large network became shorter. And shorter, to the point that the batch preprocessing time became a big bottleneck of the entire workflow. And if you also consider that normal pipelines includes different steps. For instance, I'm here representing two very common networks, AlexNet and ResNet 50. You see that there are a lot of tasks into your feeding pipeline, into data loading pipeline to manipulate your data before the training of the network. So you might go through a resizing of the image, an augmentation of the colors, a cropping, a mirroring. So there are different steps that usually take place on the CPU. So we do have complex I/O pipeline in most of the cases. And if you take those pipelines, those networks, and you start doing some performance tests, although the model are capable to scale linearly across multiple GPUs, what you get in practice is less performance. So you don't really manage to get the, the roof of your performance plane, because what happens here is that you are really behind the capability of the system, because the systems are not efficient enough to feed the GPUs with enough data and to batch the data towards the model. The main issues connected to this bottleneck is the ratio between the CPU and the GPU. So you can see on the left DGX1 with Volta 100, on the right DGX2 with the 16 Volta 100, and the ratio in this case, just to give you an example, between the CPU and the GPUs is 5 in the case of DGX1 and 3 in the case of DGX2. So this means that you have less CPUs to create and build and fill up the pipeline, the data pipeline. So this is something that you have to really take in consideration while training your networks, especially if you have a large data set and you have a deep neural network. In order to overcome the bottlenecks due to the data loading, NVIDIA developed this open source library, which is called DALI. It's a production ready software to the rescue to solve these kind of issues. The NVIDIA DALI library sits between the training data, so your hard storage, and the model. So the goal of the library is to make the data loading pipeline be efficient enough to keep the GPU busy and batch the data to the model. The DALI library can be used within different deep learning frameworks from MXNet to TensorFlow seamlessly. So before DALI was introduced, this was the pipeline. So the data loading pipeline, from the loading of the data, the decoding, the resizing, the augmentation, and then the training. Okay, the images go across the top path. So you have the JPEG, then you decode, and then you have the raw data, resize, augmentation, and these tasks were performed on the CPU, while the labels could be directly go from the loader to the training, to the model. With DALI, with the introduction of DALI, some of these tasks can be also executed on the GPU. And this has two main effects. The first is that you keep the data on the GPU memory directly, okay, so to start the training on, and some special activities such as the resizing or the augmentation can be executed on the GPU without moving back and forth both between the CPU and the GPU. As I was saying before, it's very easy to integrate DALI into most common deep learning frameworks, and I will show you some code snippets on how to do that. I will use PyTorch as a reference framework. That is the framework that we are using for the NVAITC toolkit. So this is a common pipeline. So this is a data pipeline that you have to create. You should just tell the system where the data is, what you want to do with the data, which kind of augmentation you want to apply, and if you want to resize or crop or do any other manipulation. Okay, and then at the end you have to define what the data pipeline is. So there is an initialization phase where you really define how the pipeline should be structured, what are the steps that the pipeline should go across. Okay, you have to fill the pipeline with a file reader. Then you have to tell if you want to do the padding on how to decode the data, for instance, with the image decoder, if you want to resize it or crop or normalize, or maybe if you want to really change the saturation of the channels of your images. Then you define the graph just to tell the pipeline in which sequence the steps should come. Okay, you first read, of course, then you do the decoding, the resizing, and then the cropping. And while initializing the pipeline, you can also tell DALI, please perform, if possible, this task on the GPU rather than on the CPU. Okay, and you can also say it's a mixed execution. So you start with the CPU and then you conclude with the GPU. After defining the graph, you can really build a pipeline. At this step, DALI simply checks if what you told into the initialization phase can be really implemented. So if the data is in the right location, if you can really crop, if there are all the functionalities available that you are asking for. Okay, you build the pipeline and basically you tell DALI, okay, the pipe is ready to be fed, and then to provide data, to batch data towards the model. As I was saying at the beginning, you can define different pipeline operators. The input, of course, of your data, and the CPUs really play a very important role here because it's a task that is performed by the CPU, reading the data from the hard drive up to the main memory. Then you can decode the data from, for instance, JPEG format to a RAW. And this is an operation that can be executed partially on the CPU and partially on the GPU. While loading files from the hard drive and decode them, you can tell DALI to resize the shape of the data. In this case, we are using a cropping and interpolation, the triangular interpolation, to resize the data sets. And then do some manipulation, some transformation, in this case, a cropping, mirroring, and normalization of the colors, for instance, or a coin flip. And then finally you run the pipeline. What you basically do, you create a pipe, then attach an iterator to that pipe and start iterating over the batch, okay, in your training loop. And as soon as you iterate, DALI loads the data from the storage and feed the model. So, but DALI also works in a multi-GPU environment. What does that mean? When you read the data from the storage, you have to tell DALI where to place that specific batch. And you can do that using a sharding technique. You have to basically tell DALI, for instance, if you're using Orvot, each task will take an ID, a device ID, okay, to be identified within the pool or the GPUs that you are using. You can tell DALI, please, I am the device number 1, for instance, give me shard number 1, or how many shards should I receive. So as you can see, if you have a data set, you might have 4 different shards because, for instance, you are using 4 GPUs to run the training on. And according to the colors, that specific shard will be assigned to a specific GPU. In this case, shard 0, green, will be placed on GPU number 0, and so on and so forth. So 1, 1, 2, 2, 3, 3. Okay, this is a technique to tell DALI on how to distribute the data across your resources. And of course, you can do you can manipulate, or you can do more advanced. You can implement more advanced techniques for data distribution. Okay, this is the common one, the basic one, the sharding. What is important with DALI that you can also do prefetching. So you can start prefetching data while the training of your network is going ahead. And why this is possible? Because this is a common, let's say, step of sequence that you go across every epoch. So you do batch pre-processing, the forward pass, the backward pass, the gradient reduction, and the weights update, for instance. This is the step number 0, for instance. This is the first step that you go across. But why you are doing the forward and the backward propagation, for instance, you can start prefetch data for the next step, okay, for the step x+1. So this is something that DALI is capable to handle. So it's capable to start feeding the data, keeping the data from the storage to feed the next step. This is the reason why this is possible, is because the backward pass is executed on the GPU, while the initial step, the loading, for instance, of the data, can be executed on the CPUs that in this specific moment are idle. What happened within DALI is that DALI is capable to create different buffers that you can tune how much big they should be to create queues, prefetching queues. So training 1, training 2, and training 3, these are the steps of your training loop. You can start doing batching, for instance. You can create a sort of parallel pipeline for prefetching data. But DALI can not only read images from the disk and batch into the tensor, into the model, it can also perform various augmentations on data to improve the results. And I'm showing you a paper here that did the performance across 3 different networks, Inception version 4, ResNet, and DenseNet. As you can see, in orange is the result, is the accuracy that you get without augmenting the data. So you have the orange and the gray area without augmenting the data. But if you use the augmentation with the training and augmentation with the testing, you see how the accuracy increase. So the blue line is the augmentation including training and test data. The orange is the augmentation only with the training, and no augmentation without using any augmentation steps. So data augmentation is a technique that is very important, especially in those domains where there are no so images or data available, such as the medical field, for instance. So DALI supports different augmentation that you can build in your pipeline. In this case, I'm presenting you the random shuffle or the padding for the last batch. The random shuffle basically shuffle the data for the data with your batch size as soon as you read it from the storage, okay? And the shuffling is performed using a dedicated buffer. While the pad last batch is a technique that is used when the batch size or the whole training data set is larger than the number of shards. So basically, you cannot simply divide the data set by the number of shards, by the number of iterations that you get. So to avoid the DALI to create empty buffer, if you do the padding, it's capable to duplicate the data to fill up all the shards that you have. Okay, this also improve. It's a technique, a sort of data augmentation technique that can really improve the accuracy of your model. You can see on this slide all the features that DALI supports for data augmentation. The list includes the spheering, the saturation of the color, the rotation, the jittering filter, the brightness, the flipping, the contrast. So these are all the features that you can automatically enable while loading the data. In terms of performance, this is a training across different boxes of the ResNet 50. Of course, the more data you have, the better performance DALI delivers. In the sense that if you have a small model with a not so big data set, DALI will not provide any significant boost with respect to a normal loader such as Torch Vision. But the more data you have, especially the more files you have to read from the system, the more benefit you will get from DALI. So, and in this case, you can see how many images per second you can get from the hard drive. I mean, using without a native pipeline, between a native pipeline, so without using DALI and with DALI. So, and if you see in the first 2 bars on the left, this is the DGX2, where you have 16 GPUs available with a lower ratio between CPU and GPU. So this might be, from the CPU point of view, from the data loading point of view, this is a very bad condition because you don't have so many CPUs available to feed the pipeline. But in reality, what happens if you use the DALI library, you can really overcome this limitation. and you can implement all the prefetching technique, all the mixed pipelines to run tasks across the CPU and on the GPUs seamlessly, so you can really get a factor or two in performance as a speed up. So just to give you a recap of what DALI does, so you can, it's a fast data processing library for accelerating deep learning. So it's capable to create a pipeline to accelerate the way the data is moved from the storage to the model. It's capable to combine different tasks, including data augmentation, and supports, of course, the CPU and the GPUs, because you can run tasks, we can decide which task should be executed on the CPU rather than on the GPUs. But of course, the more tasks you are capable to bring on the GPUs, the faster you will go. It's flexible in the sense that support different configuration, different operators. You can create also your own custom operators. For instance, if you have a dedicated data set with a specific binary format, you can develop your own operator in C++ because DALI provides a C++ API to get the data from the storage. So this is a very important extension point. We support natively different data formats, the record IO or the TF records for TensorFlow, for instance, Coco, HVAC, the JPEG, of course, and an API in Python and C++ to create and run your pipeline, but also to create your own specific data loader. Yeah, there is a lot of material available online with a lot of examples that you can get profit from, and how to read the data in various framework, how to create customs operator, and how to build a pipeline, and more importantly, how to combine the multi-GPU aspect with the data loading pre-processing phase. So this is what we did in our NVIDIA AI Technology Center toolkit that will be made available. So we try to combine all these features together and show how they can really bring performance boost to your workloads. And with this slide, my presentation ends. Many thanks for listening, and please reach out for any question. Thank you very much.